I invite Professor Mola Banerjee to chair the next session to be delivered, the talk delivered to be delivered by Professor S. Mukhopadhyay.
Thank you, Professor Shom. It is my pleasure to introduce Professor Santwana Mukhopadhyay. Santwana Mukhopadhyay is currently professor in the Department of Mathematical Sciences at IIT BHU. She has 30 years of research experience and 15 years of teaching experience. Her research interest mainly focused on mathematical modeling on coupled thermomechanical problems, non-Fourier heat conduction, fractional order thermoelasticity. She has a very good number of publications. As of now, more than 100 research articles she has published. Professor Mukhopadhyay has guided more than 8 PhD students. And currently, she is Associate Dean of Academic Affairs at IIT BHU. Now, I request Professor Mukhopadhyay to deliver his invited talk, and title of her talk will be Mathematical Analysis of a Recent Heat Conduction Model, Domain of Influence Result. Professor Mukhopadhyay, now floor is open to you.
Thank you.
Dr.
Thank
Malay,
you,
Dr. Malay.
Yeah.
Hello, Dr. Malay.
Yeah.
Madam is our institute में asset. She is an asset.
Yeah, I know. Actually, I heard about her from Professor Godai in our department.
Yes.
She visited to as an external expert of one of my.
Yeah, I know. Yeah.
Certainly, yeah.
Okay, so thank you, Professor Banerjee, for nice introduction, and I'm really happy that you are sharing the session when I deliver my lecture. So first, let me try whether my presentation of my slides is in order or not. 1 minute, please. I think morning it was all right.
Not visible. Otherwise, you can send me that.
No, I think I should get it. It is not coming to the picture. Actually.
If the network is slow, it may not come.
Network is all right, but that window I am not getting. A minute.
Rather, you can send it to
okay, no, it is there now. Okay, sorry. I think now. I think now it is fine. Is it all right now?
Yes, it is coming.
Yes, it is coming.
Okay,
it is coming.
Okay.
And please go to full screen.
I'm going there. Yes, so it is fine, I think.
Yes, please.
Okay. So thank you very much. I am also thankful to Professor Som, who has kindly given me invitation and giving me the scope to present my talk. So this talk is actually, my plan is today to introduce a particular topic, which is a very useful and interesting topic in today's time. That is the mathematical analysis of a particular heat conduction model and through the domain of influence results by applying it to that. So as we all agree that in today's time, mathematics is being used as a tool rather than a subject in the interdisciplinary research work. And it has allowed many advances, as we are seeing also through this conference, that it has allowed many advances in tackling several real-world problems. Even modern technologies in medicine, recent developments in computer science and communication, the fast growing of engineering, all are owed to mathematics to a great extent, as we can understand. My purpose here is to show that how mathematical analysis can be helpful to understand a real-world coupled thermomechanical problem. So the plan of my talk is like this, that we all are familiar about the Fourier law of heat conduction, and I will show that maybe many of you are aware about the drawbacks which are undergone, which has been realized by extensive research work in last few decades, the drawbacks in the Fourier law. And therefore, obviously that researchers have developed certain non-classical heat conduction models. So I would like to give some of the models, at least I will introduce, and I will talk about those models. And then I have my purpose today that about a particular recent particular model which has been very recently proposed, that is the Murray-Gibson-Thompson heat conduction model. And now we will apply this model to a particular coupled thermomechanical problem, and we will show that how mathematical analysis can be helpful to understand the state of the status of this model as a modified model of this Fourier's law of heat conduction. And also we'll also show some more things through this analysis so that we can address some of the future issues which are really thought-provoking. So as we all know that a very familiar and well-established law, that is the Fourier law, which states that for a homogeneous and isotropic medium, if we consider, then it will be that QRT is equal to minus K grad of T. So this implies that if there is a temperature gradient at a point R at time T, then there will be heat flow, and that will satisfy this law, that is Q equal to minus K grad T, or we can say in index notation that Qy equal to minus K T comma I, where Q is the heat flux vector, grad T is the temperature gradient, and T is the temperature, of course, and K is the thermal conductivity, which is a material property of the medium. And we also have the energy equation, that is divergence Q plus capital Q, where Q is the heat source, is equal to rho C T dot, where rho and C are the specific density and specific heat at constant strain of the medium. Here we are considering the homogeneous and isotropic, and if we consider the non-homogeneous or not isotropic, like anisotropic medium, then equation can be changed accordingly. Now, if we have this equation, then if we apply it, if we combine these two equations, then of course we are getting the most familiar equation, that is called the diffusion equation or heat conduction equation in the form 3. That is K del square T equal to rho C T dot plus minus Q, where dot operator dot is used here to denote that the time derivative. Now, this Fourier law of heat conduction equation, which is also familiarly called as the diffusion equation, have been widely and successfully applied to the conventional engineering heat conduction problems. However, by several experimental as well as theoretical studies during last few decades, it has been realized that Fourier law is applicable to the problems that involve large spatial dimension and long time response. However, it yields unacceptable results in the situation that involve extreme thermal gradients, high heat flux condition, and also short time behavior, such as laser material interactions. And also in recent time, that heat conduction of many nanoscale devices, because the technology has been advanced to a great level, so that time we are also observing and it is available in the literature, that heat conduction of many nanoscale devices demonstrate certain distinct phenomena like size effects, etc., like in thin film structure, which are not captured by the conventional Fourier's law. And these are lots of review articles and books are available, and research papers. We can see all these points are mentioned. Now, before I go to that, this is the drawback we are observing. Means the prediction with respect to the prediction, but before that, it is very interesting to note that as we can see here, this equation 1, that is the Fourier's law, says that Q equal to minus K grad T. So we can say that this law of heat conduction have this implies that if there is a sudden change of temperature is made at some point of a body, then it will be felt instantaneously everywhere, though with exponentially small amplitudes at distant points. In a loose manner, we can say that diffusion gives rise to infinite speed of propagation. Now, it is also interesting to note at this point that Maxwell, in long back in 1867, while doing his experiment for kinetic gases, that he has postulated for the first time the occurrence of wave-type heat flow. And he suggested that the thermal disturbance is a wave-like phenomena rather than diffusion phenomena. And he only indicated the modification of Fourier law for the first time that we can find out in literature if we go through. So obviously, because of that, that not only this one, but after certain time and many of the predictions through experimental results, since this observation was observed, so therefore people have started modifying this Fourier law or thought theoretically, and also people are thinking what can be done. So we can understand this is the first non-Fourier heat conduction law has been proposed, though it was completely theoretically, that a generalized model of heat conduction where he has written for a homogeneous and isotopic material, that is just a modification of equation 1 in the model in the form that Q plus tau del Q del T equal to minus K grad T. Here the purpose is that, here the meaning, we can understand this, that 1 plus tau del L T of Q equal to minus K grad T. So we can understand that an additional parameter tau, which is of course a non-negative parameter assumed by them, that and also termed as a thermal relaxation time parameter, and it can be assumed that it is the time lag needed to establish the steady state of heat conduction in a material element when a temperature gradient is suddenly imposed on that element. So this tau is a new parameter here, and this is called as the CV equation, because Catenio and Verner, though both of them have given independently, not a joint work, but independently both of them have thought of modifying the Fourier law in this particular way. And this is also called as the Maxwell-Catenio law, because this modification has been made as per the prediction made by the Maxwell. So, and it admits the fact that heat flux is not instantaneous effect of temperature gradient. And it, of course, whenever we put that tau equal to 0, then we are going back to the Fourier law. So that's why we can say that it carries the combined diffusion and wave-like behavior of heat transport. And this tau after that, and not only that, but because of this equation, this modification in the Fourier law, we can say that the corresponding heat conduction equation, what we have observed in earlier, that is equation 3, that what we call as the diffusion equation. So that has taken a different form. That is because of this additional parameter tau, we are getting it in the form additional term rho C tau del L T, or the rho CV tau del 2T del T2. That is the second order time derivative is here. And of course, we can see that easily that this is a hyperbolic type equation, and it is not a so-called diffusion equation. So it is like a wave-like equation, and that's why it is called a wave-like thermal signal. And we can understand that the propagation speed also v equal to minus root over of k by rho c tau, where tau, if I consider tau to be greater than 0, then of course we are getting that all material parameters are involved in the speed, and that is finite. But whenever we put tau equal to 0, then of course the speed is becoming to be infinite. So theoretically, that drawback of Fourier law we can understand from here also, and this first modification was made. And we can see that, later on, after this modification was given experimentally, also people have observed that there is a great difference in the results when we apply this equation 5 as compared to equation earlier diffusion heat conduction equation. And experimental method of evaluating tau is also available, and many values of tau is there. So for many materials, the value of tau has been predicted. And in that literature that review articles I mentioned, one can go and see that the value of tau, it has been observed, is to be very small for the material, for metals. And it ranges from 10 to the power minus 11 to 10 to the minus 14. Whereas for processed meat or for many material, it can be even in the order of second. So therefore, tau can vary from the value 1 or 10 or more than one value 1 to 10 to the power minus 15 for the metals. And also for many other material, it can go beyond that. So now after that, gradually it has further been observed that both the diffusion model, that is the Fourier model, and CV model cannot describe even the first ancient process of heat conduction, heat transfer in the thin film-like structure. And because there we have observed that both the equations are, the result do not match with this prediction by the CV model as well as for the Fourier model. And that's why people thought of introducing the microstructural effects in the heat conduction process, and that also we can see lots of papers available, research works made by the several pioneering research work, that in recent times it has been observed that in high rate heating, when the response time becomes even shorter, like it's say in the range of femtosecond, then the non-equilibrium thermodynamic transition and the microscopic effects, that these microscopic effects are basically due to the phonon interaction, electron interaction, phonon scattering, etc., to the energy exchange during the heat transport process. These microscopic effects becomes pronounced. So therefore, this formulation therefore becomes microscopic in nature, and even more generalization of heat conduction therefore came into existence because of this understanding. So many other modification of Fourier law has been proposed in few decades, as I have mentioned already. But I will discuss particularly few models today, like Green and Nagzi during their study 1991 to 93, they have developed the heat conduction equation by introducing nu as a new constitutive variable, where nu is termed as a thermal displacement by them, because nu dot is temperature T, where T is the temperature. And they have introduced the modified Fourier law in the context in this. They are actually given many models, there are research series of papers are published by these two authors, Green and Nagdi, where Green is a mechanical engineer and Nagdi is PM Nagdi is the mathematician. And their work, from their work we can see they have thought of that in the Fourier law can be expressed in this particular most generalized form, that is called as GN or Green-Nagdi 3 model, that is Q equal to minus K grad T plus K star grad of nu, where this nu is the thermal displacement and nu dot is T. And so therefore this K star is another material parameter they have introduced, and where I want to give a brief idea of what is the basis of reducing or modifying the Fourier in this particular way. If you look at the Catenio-Carnot equation, that Q plus tau del Q del T equal to minus K grad T, where K, if tau is tau need not be very small all the time for many materials, it can be even larger. So therefore, if I write down this equation, so then this particular equation K star, because this K star they only have given the name as the conductivity rate, so that means K has the dimension like K by T. So that is why where if for a particular material this tau, that is the thermal relaxation time, is much larger, then in this case we can see that K star will be much higher and as compared to K, where K thermal conductivity. But for many material it can happen that K is much larger as compared to K star. So we can see here that if I assume K star is equal to much smaller than K, that means neglected, then we are getting again the Fourier law. But when if for somehow that K is much smaller, that is conductivity rate is much larger, then in that case we can get that Q is equal to minus K star grad nu, or Q dot is equal to minus K star grad of T, because nu dot is T. So then this equation will take the form of a different form of heat conduction, like we can understand from here that this equation, if I apply and if I combine with the energy equation, then we can get the corresponding heat conduction equation in this form. So here we can see that if K star is much larger as compared to K, such that K star is K is almost 0, so then only we will have this equation that will be again wave type equation. It may give us the purpose wave type heat transport. Whereas now whenever K is much larger than K star, then it will be again Fourier, and that means it is a diffusion type of equation. And again, very recently, one more on the basis of this equation, because this equation today only we'll see that through our analysis, that this equation, if I consider the most generalized form, this is the most general form and considers a large class of material, and a wide range of problems can be solved if I consider equation 6 as the heat conduction law. So this today we will discover that this equation, again, if we go through, then this also can have some limitation, whereas theoretical limitation may not be there in the case when K star is much larger as compared to K. So we so therefore by thinking about that idea, maybe that modification recently we can have that that we are writing in here only we are introducing, there is no, though it is a modification of Fourier law, but we are not observing here the introduction of or the existence of any relaxation parameter here. Like in the first model, we have seen that there is a relaxation parameter tau. So here, if I introduce the relaxation parameter, which is also termed as a phase lag, so then we can understand that modification by Murray, Gibson, and Thomson has been given in this way, that 1 plus tau q del T of that heat flux q is equal to minus K grad T plus K star of grad of nu. So this we can see, understand that this modification may be on the basis of the modification of the Green-Nagdi model of heat conduction. So here is the K star is the same material parameter. It is termed as a thermal conductivity rate. So this this modification. So now my purpose today is that we can apply this type of this modification of so many modifications are proposed. So how mathematically we can analyze and what is the status of this equation in terms of the modification. So that is the purpose. So this Murray, Gibson, Thomson particularly has been analyzed by in a detailed way, and qualitative analysis for this particular model has been given by one great mathematician, that is Quintanilla. And he has applied this to coupled thermomechanical problem, and also he has analyzed this even this equation itself, heat conduction model, and he has shown that this equation can be stable or unstable in when this K star and tau q, where tau q is the phase lag or thermal relaxation parameter, whatever the name we will give, and K is the conductivity and K star is the conductivity rate. So they have shown in a paper that if these material parameters are satisfying this particular form, that K is greater than or equal to K star tau, or tau q satisfies this rule, that tau q is less than equal to K by K star, then only it is a meaningful equation, mathematically consistent equation, and gives stable solution. Otherwise, it is unstable. So this mathematical analysis has been given for this heat conduction model, which is termed as a Murray, Gibson, Thomson equation. So today my plan is that we can apply it to show that we can even apply for a coupled dynamical thermomechanical problem, and we can see whether this model or this modification is in order or not. And from there also we can understand that just from mathematical point of view, by giving our main logic, that whether this model, and if I ignore K or K star or tau q, then what will be the status. So that is the purpose today. And so for that, I have to tell something that what I am going to do, that coupled dynamical thermomechanical problem, I am going to apply this equation. So for that little bit, I should tell that this thermomechanical problem or the theory of thermoelasticity is actually concerned with predicting the thermomechanical behavior of any elastic solid, and hence deals with the dynamical system whose interactions with the surrounding include not only mechanical work or external work, but also exchange of heat. So there will be a coupling effect of both. Means if a material is subjected to mechanical condition, then there will be a change in the temperature content of the material, as well as when the material will be given the externally supply of heat, then also there will be mechanical change. And we'll consider the mechanical and thermal interaction inside the medium, so that governing equations also has to be consistent with both the mechanical point of view and the theory of elasticity as well as theory of heat conduction. So that's why it is this thermoelasticity is a generalization of both the theory of elasticity and the theory of heat conduction in solids, by incorporating the interactions between the strain or the mechanical strain and the temperature distribution of the material. And here also you can see that the role of mathematics is really great, that whenever we'll apply with the help of the laws of thermodynamics, because the equations will be completely changed and modified or generalized, because here both the theory we have to apply simultaneously and we have to derive the equations, so that these basic equations of coupled thermoelasticity will be derived by the laws of thermodynamics, concept of Helmholtz free energy function, and obviously the mathematical manipulation, nothing else. After we go apply the laws of thermodynamics and the other concept of thermodynamical entities, then we'll see the only mathematics after that will play the role, and they will derive the governing equations. And here also we'll see the heat conduction equation will play very important role. So, like as I said, that my plan is to derive the equation, though I had the equations, how we can derive these equations by applying laws of thermodynamics and concept of Helmholtz free energy function. But I have, I think it will take a lot of time. So therefore, I will just take up, I will say that equations will be derived in this way by applying those conditions. Will not show how they are derived, but anyone, if somebody is interested, we can give the idea or give the detailed manipulations how the equations are derived in this particular form. So what we are considering here, that one isotropic medium means everywhere the properties are same in every direction. So the every plane or direction. So this isotropic and homogeneous thermoelastic material we are considering, and we are considering that this is enclosed by the closure of the bounded open connected set, and let E bar denote the closure of this domain, so that boundary and the interior is denoted by E of E bar are classified as boundary is, let's say, delta E. I have given the notation, and E is the inside. And then in three-dimensional Euclidean space, so considering rectangular coordinate system and applying the theory of heat conduction, as I said, and theory of elasticity simultaneously, we'll see the equations will be governed in this way. So little bit, let me tell. Here, now these are when lots of material parameters are involved, because here theory of elasticity and theory of heat conduction are applied here. So we can see that here, let's say theta is the temperature above reference temperature, theta 0. So that means theta is T minus theta 0, where theta 0 is the reference temperature we have thought of. So then if I ignore this third term, like we are having three terms in the left hand side. So this mu and lambda are both are elastic parameters, and u is the displacement component. Uy are the components of displacement, and uy comma j, like if I consider one-dimensional problem, here we are considering three-dimensional problem. So in case we are considering only the one-dimensional problem, that time the equation will be just simply modified by when we consider no effect of temperature is there. That is the wave equation. Like here, that in that case it will be just uy will be u, let's say, and uy comma j, that notation is used to denote the spatial derivative. So therefore, if uy is just u we have in a x direction, so then it will be del 2u del x2, mu del 2u del x2, and here also lambda plus mu del 2 del x2. So that means total overall lambda plus twice mu del 2 del x2 is equal to rho del 2u del t2. So that is double derivative, time derivative for u. So this equation, in absence of minus beta theta comma I, will have just the wave equation. But since here we are considering three-dimensional problem, and also the coupling with the temperature field, so that's why this term is also there, and this term is nothing but due to the thermal stress involved in the whole system. Because thermal stress means because we are considering the temperature effect, so the stress will be developed, that is called as thermal stress, and total stress is that elastic as well as thermal stress, so total stress. And this equation is nothing but the modification of the second law of motion. And similarly, heat conduction equation also has been modified, because here now we are having that displacement part, that is the elastic part, is also involved, combined with the heat equation. So that we can understand that if we this uy part, if I remove, then we'll get the same type of heat conduction equation what we have observed for Mori-Gibson-Thomson equation. So these two are the governing equations we are considering. So here we can understand that we have combined the elastic as well as theory of heat conduction for a problem, and we are applying here Mori-Gibson-Thomson equation. So mainly we are having basic governing equations which are coupled. We are having two, and it is a dynamical problem in the sense time derivative is also there. And this beta is called here. It is also a material parameter. It is thermoelastic parameter, because here this beta for isotopic medium, it has the value for it has 3 lambda plus 2 mu, something like that. So this has alpha t. So this has the elastic property as well as thermal. So that's why this parameter is termed as a thermoelastic parameter. And now what in this particular work we will show that we can, if we will derive that for a finite time t greater than 0 and a bounded support of thermomechanical loading, means we will apply some thermal as well as mechanical loading to this system what we have considered, and we'll see that due to this support of thermomechanical loading, if we give a bounded support of this loading, then the thermoelastic disturbance that will be generated by the pair of temperature and a potential, though here we are having displacement component, but we will later on, for our mathematical simplicity, we'll transfer it to the, we'll see that existence of potential function. So therefore, by this disturbance, because of this thermoelastic loading, the disturbance what we will get, that thermal disturbance generated by this temperature as well as displacement or potential, whatever you say, in a body will vanish outside a bounded domain. And that domain, and this domain, so it will vanish outside a bounded domain. So after that, there is no existence of the effect of this thermomechanical loading will not be there. This means this domain where in which we are having this existence, that is, we can say as the domain of influence, and this domain of influence is finite only for MGT model. So that only we can show mathematically that here this modification of this equation has been considered, as well as this coupling has been considered. And in this case, we will see only if I consider this full form of equation 11 and equation 10, then only we'll see this domain of influence will be finite. But it is not finite for the classical model or GN3 model. So GN3 means Green-Nagdi model. When it will be? Because that time tau q will be 0. And the classical model means K star also will be 0. So in that case, we'll see that we'll not get the bounded support of this, that mathematically by applying to this couple problem we can show. And not only that, we will also measure that what can be the maximum speed of disturbance propagation and how it is dependent on the material parameters. Because here all our material parameters, they are each of every parameter is playing a role here to constitute the governing equations, and we'll see that this domain is highly dependent. This domain of influence will be highly dependent on the material parameters. And also we can of course say that though we have considered a couple problem, means this overall governing equation, the system of governing equations, we can prove this implies that hyperbolicity of this heat conduction MGT theory by indicating the finite speed of propagation of thermal waves. So what it says, that also little bit of that we'll see, and this is the main idea here. Since we are having so many material parameters and all these things, and a bit from the realistic point of view, these material constants, we can assume that they are all positive and nothing wrong in that. That is always happen in most of the material. So these material parameters we are considering that they are having this property that they are positive. And also, as I said, that we will consider that Ty equal to phi comma I, where phi is considered as a scalar field, that is the potential for the displacement field. So then these equations will be modified to this instead of u, what we are here, it will be transferred to the phi and theta. Theta is of course the temperature. So this those equations are transferred to phi and theta. And they are of course that this in this domain that t, here cross t means for time, and E is the interior part of this body we have considered. And also because of so many parameters are involved here, we have considered this non-dimensionality. If I use, then this equation will be bit simpler, and this simpler form has been taken. So here we can see so many parameters. All material parameters are basically converted to a particular parameter epsilon, where epsilon is basically for most of the material very small value, and this is called as a thermoelastic coupling constant, because here it is having epsilon is beta is there, theta 0 is the reference temperature is there, rho is the density, and C1 is nothing but lambda plus 2 mu by rho, and Cv is the specific heat. So therefore we can see here it is a thermoelastic coupling constant. And whenever epsilon in this equation, whatever we have written, if I consider this epsilon is 0, so then in that case it will be only decoupled. So that's why it is a thermoelastic coupling constant, and equations are manipulated in such a way that we are getting the simpler form of the equations. And now since we are going to show that domain of influence for due to the application of some thermomechanical loading, so of course we have to consider the conditions, and more general, not the homogeneous initial conditions we have considered, but we have considered the general initial conditions, that theta. Here the main that effect here we can see the equations are having the effect, means that due to the disturbance are a pair of theta and phi. So the conditions we are prescribing in this particular way. So initially we are having some values are that functions are there, and also the boundary we are considering some such type of boundary condition with respect to theta and with respect to phi. We have considered on the boundary that some temperature is prescribed, and some the function that is in terms of displacement or stress, whatever we want, we can give the boundary condition in terms of mechanical. So we have given both the thermal as well as mechanical boundary conditions and initial conditions. We can consider 0, but here we have considered the general type of condition. Now, what do we mean by what is the purpose of this study, and what do we mean by this domain of influence? A little bit more we can understand if I go through the two definitions. That let us consider that at a finite time t, we are considering the set d0t. And this d0t, though they are found, that is dependent on x, but we are at any particular time t we are considering. So this is considered as a support of the thermomechanical load for the present system of equations. Like we are considering if x belongs to E bar. So when it is 1, when x is interior point, that time at least one of these initial conditions are non-zero. That means some condition is there. And similarly, when the point is in boundary, so at least some conditions are there, that is either theta dash or g dash is non-zero. So that means some disturbance we are creating through these conditions inside the body. So that's why it is called the support of the thermomechanical load. What we are thinking that is there means the material is subjected to temperature and boundary mechanical condition, or vice versa, or and both. So in this case, we are considering some disturbance has been created. So the material, this disturbance will propagate through the body. Now, on this d0t is the support of the load, that is the cause of the disturbance, and we are having definition 2. It can be called as a domain of influence, means we are considering an open ball omega, which is centered at x, and with centered at x and radius nu t, where nu is any real parameter. And from that, for the above thermomechanical load d0t, what we have considered, we are considering this set dt is equal to x belonging to this closure of E, such that this one in the intersection of d0t is not equal to phi. So that means in language we can say this is the domain of influence. This implies that dt defines the set of all points of E bar which can be accessed by this thermomechanical disturbance what we have created through d0t, accessed by this thermomechanical disturbance propagating from d0t with the speed not greater than nu. So if you can say that we can set an optimality from the nu, that nu is having some maximum value, so that this disturbance will not propagate, will propagate with the speed that is not greater than nu, but it has the maximum speed nu. So then dt is that particular set of points up to which the disturbance will reach. So that's why it is called the domain of influence. So now here, just at least statement is more useful here. What we are telling that before going to the main result, we are main theorem, we are getting that one theoretical analysis we have done, that is called the main result. On the basis of the equation, here the governing equations are very important. We are having 15 and 16 after applying the potential. So what we say here, that let theta and phi is the phi.
Sorry, Professor Mukhopadhyay.
Yeah.
I think we are running late. Could you please conclude within 5 minutes?
Okay, so maybe I will just say about what has been observed here, so because that is an important, and maybe very quickly I will say, because main point is the important here, that what we say, that if theta and phi and theta is the solution of the mixed problem, then we are having this one identity we have created here. This is a mathematically we have established, but where L0 lots of terms are there. These terms are defined mathematically in this way. That is basically, we can say that we have manipulated these, because they are coupled equation. These two equations are coupled equations, and we have to write down, and we have gone to a particular identity by mathematical manipulation. If we go to, then the terms, basically we have rearranged the terms, and we have got a particular identity in this way. So this implies that if theta phi is a solution of the mixed problem, and Lx is the scalar field, then such that this particular set F0 is bounded, then we are having this particular identity. And because of this identity, now we can have our main theorem. This proof is not at all needed here. So this is the domain of influence theorem. It says that if phi and theta is a solution of the problem, and if dt is the set what we have defined by equation 20 just now I have told, then the domain of influence at time t for thermomechanical load d0t given by equation 19, which has defined this d0t, then theta and phi will be 0 outside dt. So that means theta and phi will be 0 beyond dt. So that means E bar, which one is the main closure of this particular area what we have considered. So E bar minus d0t minus dt, that will be 0. So there is no effect of this cause of the thermomechanical disturbance outside the region dt. This mathematically we can show. But interestingly, that while dt we have given the speed we are talking about, so that is the nu is the speed. If we say that nu should be would be greater than equal to maximum of 1 plus epsilon 2 b0 and 1 by tau q. So that means through this manipulation we are able to obtain this value of nu, because nu should be, if nu is only just greater than maximum of these two, so this maximum means epsilon, as I said, is a very small value. So 1 plus epsilon 2, and b0 is also material parameter, and 1 by tau q. But this if also the case when b0 is less than 1 by tau q, or tau q is less than 1 by b0, so this condition is also required, and nu is greater than, if nu is greater than that, then nu is the maximum speed of the disturbance, and that is dependent on this material parameter. So if I analyze again the value of nu, that maximum 1 plus epsilon 2 b0 and 1 plus tau q. So b0 is actually dependent on k star. It is obviously somewhere it is there, that b0 here. So b0 is dependent on this parameter k star, and epsilon is thermomechanical the coupling parameter. So epsilon is also important. But b0 and 1 upon tau q is important, because this is happening whenever we are considering this MGT equation. But if MGT equation, if I put tau q is 0, so that means we can see the speed is coming to be infinite. And also if I consider b0 is also 0 and tau q is also 0, that is the Green-Nagdi model, that time also it is coming out to be infinite. So this is purely mathematics, whatever we have seen, because whatever we have done here, just by mathematically analyzing the equations and mathematical theories, it is a lot of mathematical manipulations are there. Through that manipulation, we are able to show that this heat conduction equation in the form of MGT, if we apply for thermomechanical problem, then also we can see that it cannot have any effect of any sort of disturbance if the disturbance of course is bounded. If I give, then there will not be any effect beyond a particular domain, because everywhere that all the variables or the effect will be zero. But if I use a second form of equation where this relaxation parameter is not there, or the relaxation parameter is assumed to be zero, then in that case we are getting again unrealistic nature, that it is having the infinite speed propagation or unbounded domain. That means we are giving a bounded domain of this one, but the disturbance is propagating to with infinite speed. That is obviously quite unnatural. So that this was the purpose. Like that we can also give, since we do not have much more time, so but we can also give more mathematical analysis by analyzing in a various way the forms of equation, and we can show that the modification of Fourier law has given some sort of this, that modification of this Fourier law has been is being proposed by various researchers, but it's not that all modifications are having realistic or all modifications are there. So like we have seen that if I and that is also completely highly like Quintanilla has showed that if this parameter do not satisfy this particular relation, then we cannot have mathematical consistency or stability in the solution speed. So like that we can also show that domain of influence cannot be finite in many cases, but however in some cases it will finite. So that is the future issues. We can say that Fourier law has limitations, we can understand, but although it is being widely applicable to settle lots of engineering problems, but it is not applicable to some situations, of course. But modifications also has to be in this way, and we can analyze even we have the scope to analyze Fourier law also, that whether mathematically it is mathematically it is highly consistent, but whether it is having any drawback in the sense of that. Similarly, the other models whichever have been proposed in recent times and also long back, those models are of course not free from all the limitations. The limitations are there, so that more research and more analysis is needed. Like lots of research papers are already available which has analyzed several models and showed that mathematically inconsistencies there or not, and means mathematics has a lot of scope to contribute in this direction, and to show to understand whether this or to mathematics can play a role to understand that how we can analyze the problem or investigate in such a way that in the interdisciplinary research activity what is going on, whether we can give some contribution or not. So that was the purpose here, as we have seen that these equations or the modifications are always not up to the mark. And experimentally, though we don't have any scope, that experimentally which model is giving better as compared to Fourier law, but mathematically or theoretically we can always analyze. So thank you very much.
Thank you very much, Professor Mukhopadhyay, and let us thank the speaker first. And as we are running late,
sorry, I am really sorry.
If there is any one quick question we can take, otherwise, so any quick question? Anyone wanted to ask?
Can I ask one question?
Yes,
please.
Since it is a thermoelasticity,
yeah.
can I do the unstructured boundary conditions for this kind of problem?
Unstructured boundary, yes, of course you can try. You can you can apply and you can see, but you have to be that conditions. It has to be part of the system of equations.
Yes, always it is a system of equations.
And actually,
I am telling that the practical example, when the flight is going to the heavy cloud, it faces the thermoelasticity problem in the wing. So in that case, the shear stress took place, and that it is an unstructured boundary condition. It plays that, and many of the times we have seen that the pilot is required to be reduce the height immediately when it is going to the cloud, and that's why you are getting the jerk if you are playing in that condition.
Yes,
This
yes.
is a practical example of the MGT condition. In the
Yeah.
that's why I'm asking that it is a hydrothermal elasticity, not
Yes.
the thermoelasticity.
Yeah, we can apply, we can see what's an situation, but actually, unfortunately, after the systemification, if you look at, it's not that always closed form solution we can find
Yes,
out.
because finite element method is there, na? So many.
Now, finite element method is there, but yes,
we
we
can do the
can.
finite element method. We can do the lattice Boltzmann method. We can do the wavelet analysis. So there are many other methods. So this mathematics by hand is not required as on today, because we are going towards the practical solution, not that.
Yeah, but here purpose was that that theoretically whether this is in
Theoretically,
order or
everything is
not.
established.
Because
That's why
practically you will not get the scope. A practical numerical solution will always give you the
yes,
value of that.
solution. Na? Our next time is that to design the system, because we have to design the aircraft, we have to design the missile, we have to design the bombing when
Yes.
on the flight. So
Yes.
that's the thing.
Finite element, yeah, finite element is playing a very important role here also to
That's
solve
it.
the problem.
Anyway, thank you, Professor, for giving nice talk, and hopefully that it will be in due course, your application will come forward. Okay, thank you.
Yeah,
Thank you. So let us thank the speaker once again.
Yes.
And now I hand over the session to the organizing committee.
Thank you so much.
Let me thank Professor Malay Banerjee for nicely chairing the session on the talk of Professor S. Mukhopadhyay, who has delivered a very illuminating and nice talk.